Hello, welcome back. Today we're going to continue our journey with numeration, looking at ancient systems, and we're going to get into the place value systems. So these are going to start sharing rules and setups and patterns similar to what you're used to today with our Hindu-Arabic system that we use now. These place value systems, unlike when we were looking at those hieroglyphics, those you could technically put your symbols in any order, and it's not going to matter because you just add up the values and there you go. There's the number. But with place value systems, like where you put the symbols matters. The position affects the overall value. So you'll have some kind of base, like in our case we have base 10. So all the numbers can be looked at as some variation of powers of 10. But not everybody has a base 10. We're going to look at some systems that have some different bases. And then you've got your set of symbols. So like since we're base 10, our symbols start with 0. They represent numbers from 0 through 9. So whatever your base is, your symbols are going to represent from 0 up to 1 less than that base. So like if you're base 2, like binary, you're just going to have 0 and 1, symbols for 0 and 1. Or if you're base 6, you're going to have symbols for 0, 1, 2, 3, 4, 5. It'll go like that. And then you've got your position, you've got your base, your set of symbols. More modern day, you're looking at symbols including 0 and all the counting numbers less than that base. So who had some early place value systems? Well, before we get there, just a real quick recap on the Hindu-Arabic system and how that works, just to make sure you're kind of in that right frame of mind. Again, as I mentioned earlier, we're base 10, so we have the digits that you see there, and they represent those values from 0 to 9, 9 being 1 less than our base of 10. And the positional values are all powers of 10. So the way I wrote them there, they probably don't look too familiar, but remember we have a decimal point going to the left from the decimal point. You have your 10 to the 0, like if you had a number, you'd have a decimal point right here. You have your 10 to the 0 or 1's place, your 10 to the first or 10's place, your 10 squared or hundreds place, thousands, 10,000s, then it goes 100,000, million, 10 million, 100 million, billion, it keeps going like that. And then in the other direction with those negative exponents, those are your decimal values to the right of the decimal. 10 to the negative 1 is the same thing as 1/10, so that's your tenths place. 10 to the negative 2 is the same thing as 1 over 100, so that's your hundredths place. Then you have your thousandths, your 10,000ths, 100,000ths. So you have those THS endings in that direction. But that's what you've got going on with your Hindu-Arabic system. So if you have a number in our system, let's say you have something like 283. The 3 here is in the 1's place. The 8 is in the 10's place. The 2 is in the 100's place. So by themselves, 3 represents the quantity of 3. The 8, the numeral for the 8 there represents the quantity of 8. And the numeral for 2 represents the quantity of 2. But the positions they're in affect what they truly represent. With the 3 being in the 1's place, that's 3 groups of 1. With the 8 being in the 10's place, that's 8 groups of 10. With the 2 being in the 100's place, that's 2 groups of 100. So you've really got, a 200 plus an 80 plus a 3 to give you that 283. And if you have a decimal, same kind of idea, but you also have those tenths, hundredths, thousandths you're dealing with. So like if you have 51.34, well, to the left of the decimal, you have 1's and 10's. And then to the right of the decimal, you have tenths and hundredths. So what do you got there? Well, you got 5 groups of 10. You've got 1 group of 1's, 1, 1. You've got 3 groups of tenths, and you've got 4 groups of hundredths. But remember too, fractions can be written as decimals. So three groups of 3 times 1/10, that's the same thing as 3 times 0.1. 0.1 is the same thing as 1/10. 4 times 100th, sorry, is the same thing as 4 times 0.01. So notice how the 1 keeps shifting depending on what place value you're in. It's all powers of 10. So it all involves this decimal. So you end up with 50 plus 1 plus 0.3 plus 0.04. And that all adds up to your 51.34. So that's in a nutshell what's going on here with our place value system. And to show you a little bit of history, the Hindus in India invented the 0 and other symbols, while the Arabs adopted the system as they were trading with the Hindus. So hence, that's why it's called the Hindu-Arabic system. The numerals of today took shape in the middle of the 15th century. So the numerals didn't always look the way they do now. And in fact, I believe in your book somewhere, your current book, if you're in the future from when I made this video, you might not have this chart, but in the current book, there is a chart somewhere that shows kind of the evolution, a little bit of an evolution of our numerals. Ah, yes, right now on page 191 in the current book, it's in 4.4. But this is right now as of fall 2020. So if it's another school year, it might be a different page, or it might not be in your book. But anyways, there's a cool little chart there. It shows you the symbols and how they've looked from the 12th century, 13th century, all the way through 20th century, and computer font and all that kind of stuff. So that's a pretty cool little thing to look at. And as this system was adopted, mathematics was revolutionized. Suddenly, this system was great for learning, for ease of use and learning. So it was able to spread. People were able to be educated on it and able to start computing more efficiently and effectively with it. The first people who were starting to do these computations, were called algorists. So you probably have heard the word algorithm, but here, the algorists. A lot of our words that we use in mathematics either have Greek origins or have Arabic origins. The numerals are called digits because the base 10 system was developed from counting on your fingers or your digits. So, it kind of makes sense. And then all of you, I'm sure, have taken algebra before. There was a gentleman named Al-Khwarizmi who's very essential to the history of algebra. And algebra comes from al-Jabr. It's basically talking about like the summing of wholes and parts. And all of this is from the Middle East, that's all part of that history. So as I mentioned previously, I took a history of math class when I was in college, and it was really cool because you got to see some of the pathway of how we got to where we are now with our mathematics, and how long it took humans to really develop what we're doing. But anyways, I digress. I do that. Sorry. All right, moving on. Why don't we visit the Babylonians, who around 2500 BC, so they weren't too far off from our hieroglyphics, but they developed a system. It's the oldest known numeration system that resembles place value. It's not purely place value as ours is now, but it was very close. But it's the oldest known system, and I say that because so much of history, way back when got lost. Either it wasn't recorded or got lost somehow. But they used a base of 60, so this is called a sexagesimal system. But they weren't including 0 at that point. And they were using like wet clay tablets. They could make clay using the mud and things from the riverbanks in the area. And they would use a stick, which was really, they called a reed or a stylus, but it was a stick with like a shaved end so that it came to like this flat point on the end. And they could put this put this stick into the wet clay, kind of like playing with Play-Doh, like pressing something into Play-Doh, but this clay was wet while they did it, and then it would dry. And they could angle the stick to make a thin wedge to represent 1 unit, or they could make wider wedges, like wiggle it a little bit, make wider wedges to represent 10 units. If they wanted to represent 0, they didn't have a symbol, but they would put gaps in there for that. And the system, it worked pretty well for them at the time. And we actually still see bits of it in our time in navigation, because if you think about our time, like our clock, we've divided up an hour into 60 minutes, and then we've divided a minute into 60 seconds. So when you want to look at how many seconds are in an hour, you actually are looking at 60 squared, 3,600. So you see that there. And then navigation also uses degrees, minutes, and seconds, and then still looking at those powers of 60 for the minutes and seconds parts of the breakdown for parts of degrees. And if you think about a circle, we're looking at 360 degrees, that's 60 times 6. So, that 60 is a common theme. All right, and this was the best I could do to kind of make the symbols. Your book has a little chart too. Theirs probably looks a lot better than mine, but, I'm using a computer here. I'm kind of limited. I think theirs in the book looks a lot better, but you get the idea. You can see in the book what they look like. It's pretty similar. But there's my thin wedge for 1. There's the thicker wedge for 10. And then they could do subtraction too to me that looks kind of like a torch where the flame's shaped like an arrow or something, like an Olympic torch or something. But that's the closest I could come to their subtraction symbol. All right, so let's see how this would work. All right, when we're talking about base 60, it's kind of like talking about bases of 10, but instead of doing powers of 10, like normally, we'd have our 1s place, our 10s place, our 100s place. Instead of doing that, we're going to be talking about 60 to the 0 power, which is 1, 60 to the first power, which is 60, 60 to the second power, which is 3,600. And you could keep going. You could go as high as you need to. There's no limit on how high you go. But it's all powers of 60. So if you have one of their numbers that looks like this, let's say you have a number that looks like this, like thicker wedge. Again, please bear with me. I'm doing my best here. So thicker wedge, thinner wedge, thinner wedge, thinner wedge. And then there's a gap. And then thinner wedge, thinner wedge, thinner wedge, thinner wedge again. All right. We know that thick wedge is 10, thin wedge is 1. So this is 13. Thin wedge, thin wedge, thin wedge, thin wedge. That is 4. But it's not 13 and 4 because we have to consider the place value. Since this group of 4 is in the far right position, that is 4 groups of 1. So we have to do 4 times 1. And since the group of 13 is in the next position to the left from the 1s, that's 13 groups of 60. So you have to do 13 times 60. So we do 13 times 60, we got 0, 18, that's 780, plus 4 times 1 is 4. So we're going to get 784. So 784 is the Hindu-Arabic version of what the Babylonians would have written there. So we need to first figure out with the wedges what that comes to, each group. And then we got to look at what position the group's in. And whatever the values are from the wedges, multiply that by the place value, and then add up the results. It's not really unlike what we do, Like when I talked about having a number like 354, you've got the, the numerals 3, 5, and 4 represent 3, 5, and 4, but the place value makes the 3 a lot more than just 3. We had to take the 4 and multiply by 1, we had to take the 5 and multiply by 10, and we had to take the 3 and multiply by 100 to really see what was going on there. So you really have 300 plus 50 plus 4. And that's the same concept of what's happening with the Babylonians, except we're dealing with 60s, powers of 60 instead of powers of 10. So 4 times 1 and then 13 times 60. All right, let me do another one. I know some of you are sitting there going, I don't know, this is kind of weird. That's all right. All right, I'm going to do this one. It's going to be thick wedge, thick wedge, thick wedge. And then it's the little subtraction symbol. Looks like the torch or whatever. And then it's going to be a thin wedge. So that's the best I can do with drawing it. I don't have a stylus. Well, I do have a stylus technically. It's an Apple Pencil. It's a stylus, but not the same kind they would use. Theirs would have been a stick kind of shaved down to a little flat edge. But anyhow, all right, what do we got here? So what we've got, all of this, there's no gaps. So there's no, this is all in the ones place. But notice that we have 3 thick wedges, which is 30. And then we have the subtraction symbol. And then we have the thin wedge, which is 1. So all of that just represents 29. And there you have it. So if it had been spaced out differently, that would be a whole different story. Like, what if you had, well, before I scroll down, let me do this. If you'd had thick wedge, or I'm sorry, thin wedge, thick wedge, thick wedge, thin wedge, thick wedge, subtraction symbol, and then thin wedge, thin wedge. This would be different. The spaces mean there's different place values. So let's first just look at what each numeral per se is. You have thin wedge here is 1. 2 thick wedges and a thin wedge is 21. Then thick wedge minus 2 thin wedges is 8. But this 8 is in the 60 to the 0 or 1's place. The 21 is in the 60 to the 1st or 60's place. And the 1 is in the 60 squared or 3600's place. So we're going to do 1 times 3600 plus 21 times 60 plus 8 times 1. So we've got 3600 plus what? Okay, 21 times 60, 0, 6, 12, and then 8. So we add all that up, we get 4,868. So that's how that's done. So converting from their system to ours, you figure out what the numerals are, you multiply by place values, add them up. But you probably have a growing suspicion that that's not all, and you would be correct. Because we're not just going to go from their system to ours, we're going to go from our system to theirs too. So let's see how that works. What if we have a number like 3,602 and we want to time travel back to the ancient Babylonians, and we want to show them, grab a stylus and a clay tablet and write this number. Maybe it's a secret to the future of the universe and we want to tell them so that they can save the world or something. I don't know. So what are we going to do? Well, we need to figure out what is the highest place value in Babylonian for this. Well, we've already been dealing with powers of 60, so we're still going to be dealing with that. Remember, the far right would be 60 to the 0 or 1's place, Next would be 60 to the first, or 60's place. Then you got 60 squared, or 3600's place. If we try to go any further, we're too big because we've got 3,602. 60 cubed, this would be too big. We want the biggest place value that's still less than our number. So we want to go with the 3,600. So what we're going to do is we're going to try to figure out how many groups of 3,600 are in this number. So we're going to take the original number, 3,602, and we're going to divide by 3,600. And we end up with one group in there. Then we're going to take the remainder and divide by the next place value. Well, there's 0 groups of that. And then we're going to take the remainder and divide by the next place value. And when you get to the ones, that should finish it off if it's not already finished off. So now we know the values for each place value. We figured out, well, how many groups of each are in that number, in 3,602. There's 1 group of 3,600, 0 groups of 60, 2 groups of 1. So all that's left, put it into their numerals. Write it the way they would have. So that 1, I feel like I made a mistake somewhere, but I was looking at this again. Something wasn't looking quite right. But that 1 would just be... Yeah, this should be fine. Okay. So the 1 would be a thin wedge. I think I just realized there's a... in your book, there is a nice little typo. That's why it's throwing me. All right, 0 would be a big gap, and then 2 would be two more thin wedges. In your book, they showed that as a 10 right there in the 3600s place, but that doesn't make sense because the number is 3,602, the answer that's supposed to be there. So, sorry, that just really threw me off because I was looking at that and going, that doesn't make sense. But anyways, yeah, I can pull out my calculator and double check, but I'm pretty sure my mental math is fine. Because 60 squared, 60 times 60 is 3,600, yeah. And then when you divide 3,602 by 3,600, it only goes in 1 time. So yeah, that'll be a 1 right there. And there you go. So you leave that gap in between to show 0. Because remember, they didn't have a symbol. They didn't represent 0 in their numbers. Okay, so let's do one more of those before we move on to the Aztecs. Or Mayans, sorry, not Aztecs. But let's see here. How about if we want to do 677? What if we know it's that number, but we want to put it into their numerals? Well, we've got 60 to the 0 is 1. 60 to the first is 60. And we already know 60 squared is way too big because from our previous example, we saw that 60 squared was 3,600, and that's way over 677. So we're going to start with the 60s place. We're going to divide 677 by 60 and see how many groups of 60 are in there. Oh my gosh, I got mixed up there. Sorry about that. I was jumping ahead of myself in my head. All right, so we got 11 groups of 60 there. And then the 17 remainder gets divided by the next one, but obviously when you divide by 1, you're just going to get the same number again. So easy, so fun. Okay, there we go. So we get a 17 for that. All right, so to represent 11, we can put a 10 and a 1. I like coloring it in. Sometimes coloring is a nice little stress relief when you're doing math. But anyways, you can do a 10 and a 1 for the 11. Then for 17, I mean, you could try to do a 10 and 7 ones, but that's a little long. So what you're probably going to see is instead they're going to do 20 minus 3. that'll be fewer symbols. So 20 is 2 10s. I'm not a very good drawing. I'm good at drawing. That's why I'm not an art major. Some of you that are art majors, I bow down. I cannot do that stuff. All right, and then minus, and then 3. My 1 wedges look too much like my minus signs, but you can tell my minus sign because of the little, looks like a greater than symbol on the top of it. But there you go. So 20 minus 3 would give you 17. And there you have it. So that's the Babylonians. And if you can do Babylonian, you can do Mayan. Except Mayans threw a little tiny wrench into it. I'll show you what it was. The Mayans put a little extra difficulty in, but it's not that bad when you understand why. They were from the Yucatan Peninsula in Mexico. And they had, at first it appears to be a place value system with base 20, a vigesimal system. But in the third place value, they temporarily use an 18 multiplier instead of another 20. They did a lot with their calendar, developing their calendar, and there was a lot. They had additional math symbols when it came to dates and things, and there's a lot of religious significance that was integrated into their calendar system. But they realized that a year is about 360 days. And so more than likely in that third place value area, they were doing 20 times 18 to get the 360. They were very eager to have 360 in that place value. But then beyond that, in the 4th position, 5th position, 6th position, they resume multiplying by 20. So it's like 20 to the 0 power, which is 1. 20 to the first power is 20. But then instead of 20 squared, they do 20 times 18, which is 360. And then after that, they do 360 times 20. I think that's 7,200. And then they do 7,200 times 20. So they keep that 360 in there, and then they keep multiplying by more 20s. They used dots and lines for their numerals. More than likely, that was from using like sticks and pebbles or sticks and seashells and things. And then their 0 looks a lot like a big seashell. So that's probably what they were doing. And then, like I mentioned a minute ago, they did have a holy number system with its own set of hieroglyphs for the calendars for the priests. And this is my best rendition using a computer. I apologize for the messiness of this chart, but when the PowerPoint was converted over for Notability, it shifted some things in some of these charts. So just keep in mind everything got shifted. But if you go into Canvas, the modules, you will see these charts in the PowerPoint, and they look correct in the PowerPoint. It's just something with the conversion and Notability did this. The system's actually not too bad. Like, each dot really represents 1, and each bar represents 5. So like when you get to 6, when you get to this right here, it's like 5 plus 1 or 6. So then 7 is 5 plus 2 dots. 8 is the 5 plus 3 dots, and so on. When you get to 10, it's 5 plus 5, 2 bars. So that's basically what's happening. And just like what we were just doing, you use these symbols in their correct place value to represent. All right, so let me see here. If we have a number like this, and then like this. Okay, so we can look at our chart and determine that the top one is 6 and the bottom one is 17. But we also have to consider our place value. Okay, so this is instead of reading from left to right, we're going to read like top to bottom. But the very bottom place value, that's where you have your ones place. So this is your 20 to the 0 or ones place. And then the next one up is your 20 to the first or 20s place. So you have 6 groups of 20, which is 120. And then you have your 17 groups of 1, which is 17. So you add those up, and you get 137. So that's what it is in Hindu Arabic. All right, let's do another one. You got 3 dots with 2 bars. And then you got the 0 symbol that looks kind of like a seashell to me or something. And then 2 dots. All right, so this is 13, 5, 10 plus 3. This is 0, and this is 2. Remember, each dot's like 1, each bar is like a 5. And then the 0 is that big shell-looking symbol. All right, the very bottom place value is your 20 to the 0 or 1s place. Then you got your 20 to the first or 20s place. But remember, after that, they don't have 20 squared. Instead, they have 20 times 18 or 360s place. So we're going to do 13 times 360, 0 times 20, 2 times 1. So whatever 13 times 360 is, I'm going to pull out my calculator here. You can't see me do it, but I'm going to do it real quick. 13 times 360 is 4,680. So we have 4,680 plus 0 plus 2. So we're going to get 4,682. And there you go. Okay, how about if we go the other way? How about if we start with 930, and we put it into theirs? Well, we know bottom is 20 to the 0 or 1s. Next one up is 20 to the first or 20. Next one up is 20 squared or not 20 squared, sorry. I got into a rhythm. 20 times 18, which is 360. And then if you try to do 360 times 20, that's going to be way too big. 0, 0, 12, 7,200. So, no, too big. So you're trying to find the highest place value that'll still go into 930 without being too big. So we're going to do 930 divided by 360. I'll do it down here. And that'll go in twice. And since that goes in twice, or 2, you got 2 dots. Then we're going to do the remainder of 210 divided by the 20. So you're going to get a remainder of 10. But you have the 10. So remember, that's 2 bars. And then 10 divided by 1 is still just 10. So that's another 2 bars. So this is what it would look like. It almost looks like a face with two stern mouths or something. Like 2 eyes and then 2 mouths. I don't know. But anyways, so 2 dots, 2 bars, 2 bars. All right, and then maybe we'll do one more of those. 4,000. Okay, so place values again. 20 to the 0 is 1. 20 to the first is 20. Then 20 times 18 is 360. Again, 360 times 20 is too big. That's 7,200. So don't want to do that. All right, so do 4,000 divided by 360. So you get an 11. So that's 2 bars and a dot, right? 5, 10, 11. Then you do the remainder of 40 divided by the 20. 20 times 2 is 40. Ooh, remainder 0. It's a 2, so that's 2 dots. And then as soon as you divide 0 by 1, you're still going to get 0. So So then you can use your little 0 symbol. And there you go. So to convert from our system to theirs, it required division. So if you're starting with like the Mayan numeral and you're trying to convert it to Hindu Arabic, you end up having to multiply. But if you start with the Hindu Arabic, like what we're familiar with, and want to convert to Mayan, you have to divide. And you can see that here, we had to do all that division. Whereas previously, we had to do multiplication and addition. And that's going to be true for converting between bases. That's basically what we were doing here. We were converting between different base number systems. When we get into the next lesson, we're going to be converting between other bases, like from base 10 to base 2 binary, or like from base 16 to base 10, that kind of thing. The same general rule still applies. If you're trying to convert to base 10, you're going to have to do some multiplication. If you're trying to convert from base 10 to another base, you're going to have to do some division. So that's just something to keep in mind. All right. Thank you for joining us, and I look forward to seeing you when we generalize this for other bases.